Hello, in this video we will discuss about how to determine the regioselectivity in E2 bimolecular elimination reaction. Okay, for this discussion, let us pick up one example of alkyl halide, that is CHBrCs3. This is like 2 bromopropane, and it is reacted with, say, a strong base methoxide ion. That means it can be sodium methoxide, like that. Na plus you may or you may not write. You need to understand that. Now, when we do this reaction, this is a strong base, is secondary alkyl halide, undergo E2 elimination. Now, in this process, the uh, hydrogen and halogen will be eliminated. So here the carbon in which the halogen is attached, we call that as the alpha carbon, and the carbon adjacent to this alpha carbon we call beta carbon. So this CS3 is beta carbon and this CS3 is beta carbon. Now this base can remove the hydrogen from one of the beta carbon and the halogen or the bromine from the alpha carbon, that result in the formation of alkene. Now in this process, since both of the beta carbon and hence the beta hydrogen are equivalent, you can remove any of the beta hydrogen and the halogen, it result in the same product. Say for example, if we decide to remove this beta hydrogen along with this halogen, the result will be CS2 double bond CHCS3, that is propene is the alkene product, and here you have other side product will be CS3OH plus Br minus. These are the side product. So here if you remove any of this beta hydrogen, it will result in only one product. That means there is no regioselectivity. But however, if we choose the another substrate, say for example CS3CH Br, and you have CS2CS3, this is like 2 bromobutane. In this substrate alkyl halide, you have this alpha carbon is the carbon in which this bromine is attached, is alpha carbon, and but you have the beta carbon, that is this carbon, and this carbon is the beta carbon, the adjacent to the alpha we call beta, and these beta carbon are different type. One is with the CS2, other is CS3. So these beta carbon are different. And if we react this with, again, the strong base, say CS3O minus methoxide, again, you have two possible products. If you remove the beta hydrogen from the CS3 and the bromine you remove, then the result will be CS2 double bond CH CS2 CS3. You have 1 2 3 4, it is butene, but double bond is in carbon number 1, therefore 1 butene is the product. That means we are removing the hydrogen from this CS3 hydrogen from this beta hydrogen and with the bromine. Okay, but if we remove the hydrogen from this CS2 beta hydrogen along with halogen, the result will be CS3 CH double bond CH CS3. That means you have 2 butene will be the product, another possible product. Okay, and this 2 butene product you can write in two ways. one will be as a trans, or you can put that as the cis 2 butene or trans 2 butene, whereas one butene is only one type, you have one double bond here. So these are two possible product, and the 2 butene you have two possibilities. Now the question is, and on the other side product of course is CS3OH and Br minus. The question here is, among this 1 butene and 2 butene, which one will be the major product? Okay, that means that is when we are discussing about regioselectivity. Now, to discuss about this one here, uh, we need to understand about the stability of the alkane. Again, nature is lazy, so it will try to form the product which is more stable. More stable. So stability means here, that means more stable product. That means product is obviously alkene. More stable alkene will be the major product. Major product in this type of elimination reaction, E2 reaction. More stable product will be the major product. Now the question is, how do we decide which one is more stable product? So that is when the alkene will be more stable if it has more substituents attached to it. Substituent attached will be the more stable product. More substituent attached, or in other word, a more substituted alkene will be more stable, and hence that will be the major product. Now the question is, how do we decide which one is more substituted, which one is less substituted? How can we decide that? So more substituted means larger number of substituent. So how do we decide that? When you have carbon carbon double bond, again don't forget carbon has 4 bonds. So with this carbon with the double bond, it will have two other group that needs to be attached, and the other carbon with the double bond, sp2 carbon, also needs to have two other group to be attached. If you have all these are hydrogen that is attached, so hydrogen we do not consider as the substituents, so it does not have alkyl substituent. That means it has what? No substituent. So all four are hydrogen means no substituent. So this type of alkene will be least stable. Now, so this will be less than that of if you replace one of these hydrogen by any carbon containing group, or you can say alkyl group, or say R group, then we call that as the mono-substituted product. So one is R group, any alkyl group, methyl, ethyl, propyl, butyl, any alkyl group, that will be the substituent. So this is, we call that as mono-substituted. Mono means only one substituent. So how do we decide that? Just you need to look at the carbon across the double bond, and if you have any R group, that will be the substituent. This is the mono substituted. And if you have the carbon containing double bond poses two R group, that will be disubstituted. Now 2R group can be in different position. Say you have both R group in the same carbon, that is, you can call that as geminal, and the same carbon, and there are two hydrogen. This is we call disubstituted. Disubstituted. And the other possibility of the disubstituted is carbon carbon double bond. You have two R group but on the adjacent carbon, and both R group are facing on the same side. So this is also disubstituted, but this is cis. They are on the same side. And the other possibility for the di-substituted is carbon-carbon double bond, and you have two R group, they are facing on the opposite side in the adjacent carbon, but they are facing on the opposite side. We call that as also di-substituted. Di-substituted containing two substituent, but this is trans. So you can see that there are three types of di-substituted alkene. We have one with the both R group on the same carbon, geminal, and both R group on the adjacent carbon, they are facing on the same side, we call cis, and R groups are on the opposite side, we got trans. Same. So again, based on our rule, the di-substituted are more stable than that of mono-substituted. Okay, so mono-substituted is less stable than that of any of these di-substituted. And make sure you understand this also, you understand that among the di-substituted, geminal one is less substituted than that of cis. Cis will be less substituted than that of trans. Please remember this. Okay, and the next one will be carbon-carbon double bond with three alkyl substitute. And again, it can be R or R prime. It can be any group, any carbon-containing group, and only one hydrogen. We call that as tri-substituted. And the list, so this one will be this one is better than that of di, so di will be less than that of tri. And the last one is what we call is the tetra substituted, no hydrogen, all four are R group. It can be same or different, we call that as tetra substituted. That means what? The alkene with four alkyl substituent is more stable than that of tri. Tri is better than that of di, is better than mono, and then it is no substituents. So that is how we decide the stability. Okay, this is how we decide the stability of the alkene. And this can again, now talking about the major product, if we go back to our problems in hand, in this case we saw that the one butene you have there, this carbon has two hydrogen across the double bond, two hydrogen, and has one hydrogen, so there is only one substituent, so one butene is mono substituted, whereas 2-butene has two alkyl substituent, and it has two hydrogen, and this one, the 2-butene will be major product. And in this reaction, 2-butene is about 80% and 1-butene is about 20%. So this is the major product in the regioselectivity. Okay, so this discussion again we can extend and we can discuss that as the rule. We call that as the Jet-safe rule. So Jet-safe's rule, according to this rule, okay, so the Jet-safe rule is removal of proton from beta carbon occur in E2 reaction, occur to give more stable alkene. More stable alkene. More stable alkene means, as we learned, that more substituted alkene. More substituted alkene. That is the major product. All right. So that is how we decide the product here. Say for example here, uh, we can see one example here: CS3, CS2, CS2, CH with the chlorine, and CS3. You have here 2-chloropentane. If you react with, say, hydroxide, OH minus, then we have the possibility, this is your alpha, this one is beta, this one is beta, so CS3, CS2, CS double bond CH, CS3. If you remove this beta hydrogen there, this will be the product. Like